Hello, and welcome to a digital lecture for Salt Lake Community College. This lecture will cover section 3.5 for Intro to Statistics, considering inference for a single proportion. This section will, as stated in the text, formalize how to carry out confidence intervals and hypothesis testing for a single proportion. First, when designing an experiment or observation, we say that a single event that leads to an outcome can be called a trial. If the trial has two possible outcomes, i.e. heads or tails when flipping a coin, we typically label one of those outcomes as a success and the other as a failure. A success is generally the outcome that we are interested in studying, and a failure is the outcome that is not a success. Note that in the simple example of flipping a coin, either a heads or a tails can be considered a success, and the other a failure. It does not need to be whichever event has a positive connotation. You would calculate the proportion of successes in the sample, called the sample proportion, by taking the number of successes divided by n, which is known as the sample size. Reminder that we will often strive to apply the normal distribution framework to these situations for sake of simplicity. Hypothesis testing and confidence intervals can technically be constructed on distributions that are not verified as normal, but that tends to come with more complication and also more unreliability. The sampling distribution for p hat taken from samples of size n from a population with a true proportion p is approximately normal when the data comes from a random sample or randomized experiment. The sample observations are independent, which we will verify by checking that the sample size n is less than or equal to 0.05 times the population size, capital N, and we expected to see at least 10 successes and 10 failures in our sample. We can find this by checking that n times p is greater than or equal to 10, and also the complement n times 1 minus p is greater than or equal to 10. If these conditions are met, then the sampling distribution of p hat is approximately normal, with a mean of p, and a standard error that is calculated as the square root of p times 1 minus p divided by n. Note that in every statement here, we use p, which represents the population proportion. This is often an unknown value, since we are usually trying to estimate p, and so we will need to substitute a replacement in for p. For confidence intervals, this is usually the sample proportion p hat, and for hypothesis testing, it is the null value, p sub 0, that comes from the null hypothesis statement. As for the requirement on independence, if data comes from a simple random sample and consists of less than 5% of the population, then the independence assumption is reasonable. Or, for example, if the data come from an experiment where each user was randomly assigned to the treatment or control group, and users do not interact, then the observations in each group are typically independent. On the next page, we will have some instructions for computing normal probabilities from z-scores. We will navigate to the GeoGebra probability calculator and input the mean and standard deviation accordingly from our proportions. Then indicate which type of area we want and from what value. I will demonstrate how to do this using the next example. According to the Congressional Research Service, 64.9% of Utah is federal land, owned by the federal government. 100 locations in Utah will be randomly selected and checked to see whether they are federally owned. What we should do first is describe the sampling distribution of p hat. First, the center, which is defined as the mean, which is 0.649. Next, we will need the spread of the distribution, defined by the standard error of p hat. That will be the square root of 0.649 times 1 minus 0.649 divided by the sample size of 100. That will result in a value of approximately 0.0447. Keep in mind that both the mean and the standard deviation for the sampling distribution are both decimal values. The shape of the distribution is a little bit harder to tell, and there's a little bit more that we need to dive into to do that. First, we can verify independence by claiming that the 100 locations in Utah that we have would likely be less than 5% of locations in Utah. Also, since they were randomly selected, that verifies independence for us. And to finish off normality, or our claim for normality, we can look at NP and also N times 1 minus P and ensure that both of those are greater than 10. As this statement shows, we have approximately normal because each observed location is independent of each other, since 100 locations is likely less than 5% of all locations, and they were randomly selected. And also NP, which is 100 times 0.649, is bigger than 10. And also N times 1 minus P, which is 100 times 1 minus 0.649, is also bigger than 10. With that done, now we can calculate some probabilities using specific sample proportions. We have here first the probability of p hat is less than 0.6, and we also have the probability that p hat is greater than 0.7. First, what we should do, we should always draw a picture. So I have here a normal distribution centered at the given mean of 0.649. Since we are looking for 0.6, 0.6 is less than 0.649, so I will draw it somewhere around here. And since we want the area below 0.6, I will shade this region. If we look at it numerically, we notice that 0.6 is a little bit more than 1 standard deviation away from the mean, the standard deviation or standard error being defined as 0.0477. So we should have an expectation from this. We should also be able to draw a picture for the second situation. Again, centered at 0.649. Here, though, 0.7 is above 0.649, so I'll draw it up here. Again, about 1 standard deviation away. And we want above 0.7, so we'll shade the region to the right. It is always in good practice to draw the picture first before doing any calculating. That way you know, based on the value that you get, whether it is something you expect or if it seems incorrect. Now that I have that picture drawn, we're going to go over to GeoGebra and calculate both of these values. Here I am in GeoGebra in the probability calculator. I already have here the mean demonstrated as 0.649 and the standard deviation as the square root of 0.649 times 1 minus 0.649 divided by 100. Now all I need to do is calculate the probabilities appropriately. The first probability we wanted was to find a value less than 0.6. So instead of having less than 1, which is what it defaults to, I'll change that to 0.6. And I find a value of 0.1523. Note that I have here the left-sided tail selected. If I want to do the probability that is greater than 0.7, then I will select the right tail and change this value to 0.7 instead, which gives me an answer of 0.1426. When we're back to the notes, we then have our two answers complete. We could say that our first answer here is 0.1523 from GeoGebra, and the second, 0.1426, also from GeoGebra. If you have any further questions, be sure to review the example videos or ask your instructor.